Hello everyone, hope you're doing and welcome back to my channel. Today we are at day 23 of the November till LeetCode challenge and we again have a medium question in front of us. And this question is again related to a matrix. Okay, from the last 3 days we are getting questions on matrix. Yesterday we saw something different. It was again on matrix, but we saw uh, the bit manipulation topic also getting involved in that. And today again we are having a question on matrix. Okay, so the idea here is if we see the diagrams. So basically what is happening is that we are given a 2D grid. Okay, and then we are going to shift it by 90 degrees, and then they're telling you to design the configuration of what it will look like after you shift it by 90 degrees. The idea here is that after you shift it by 90 degrees, as you can see here in this image, some of the things will start falling. Okay, so based you have to take into consideration the gravity, and then you will have to design the the way it will look like. Okay, you'll have to give the coordinates for each of the objects after the 90-degree shift. Yeah, you have to also consider the gravity you know for this. So let us see what are the things here. So if you see here, these are the three things that you have to consider. Okay, there will be a stone, there will be obstacle, and there will be empty part. Okay, the obstacle will not move. Okay, the obstacle will be that will not be affected by gravity, as simple as that. Okay, and the empty part is again, it can be occupied by a stone. Okay, if it falls, the stone is something that will be affected by gravity, remember that. And if there is space below, it will fall. Okay, we'll see the examples and let us see. So what happens is, like, after it is false, you have to give the configuration, that is you have to create another 2D array. Basically what will happen is, see here, if you see, this is a matrix. Okay, the way you're seeing it, but after it falls, basically the dimension of it changes. Okay, so you have to basically create a new matrix and then you will have to return the answer. Okay, as simple as that. So let us first quickly understand what is happening. So let us consider the first row. Remember one thing, if you have to do the changes within the input given to you, what you will have to do is, see, if you have to simulate like how the gravity will act, you'll have to think it like they will start moving towards the right. Okay, for example, if you talk about this particular stone, okay, here, this will start moving towards its right. Okay, after it falls. Okay, so why we have, like, see, after, let's say, logical imagination, right, you'll have to code your way to it. Okay, so what you can do is, see, this particular stone will move towards its right. There are two empty spaces now, and all the stones will start moving towards the right. Okay, so this is how it will look like. Okay, after simulating the 90-degree fall, the 90-degree shift and the gravity fall. Okay, so this is how it will look like. If you see here, the dark gray parts are the walls, that is, they will not be moving, they will not be impacted because of gravity, as simple as that. Okay, so that is the point here, and let us see the other examples also. And if you see here, basically, so this particular stone which you're seeing here, okay, this stone, that will fall. Okay, this is how it will be after that. Okay, and yeah, here if you see, the dimension of the matrix changes and the space between them, these two, is getting filled when they fall. Okay, as simple as that. So let us try to see what happens here. Okay, so I will show you two approaches. Basically, one approach, I will show you one of the sorting, that is, I am going to use a heap basically to get the empty places, and then I will be using it, and then we'll show another optimal approach without using any data structure as such. Okay, let us see the solution quickly. So before going to the solution, first of all, you will have to learn how do we get the matrix, that is resultant matrix, first of all. Okay, see, you will have to understand the relation between the matrix. Okay, for example, see, let us say you understood how the simulation works, you did it in the input itself, but then you have to simulate the matrix, right, the resultant matrix that has a different dimension. Then you have to transfer the values to the resultant matrix, and then you have to return that. Okay, so let's quickly understand how it works. So if you see here, like, this is, let us say, the input dimension. Okay, and this is the input dimension given to us, and this is how the output dimension will look like. Okay, so what happens here is, what I'm trying to do is, see, if you take the first row, okay, this will become the first column. Okay, this will become the first. Yeah, if you see the first row, basically after the 90-degree shift, this will become the last column. Okay, and similarly, this particular row, that is the last row, will become the first column. Okay, so that is how the shift is going to happen, and you have to do that in that way. Okay, we'll come to this when we are this part of the code, but just for your information, we are going to do this. Okay, first of all, we will make the change in the input itself, and then we will be simulating it to the resultant matrix. Okay? Let's see the code now. This approach what I'm showing you is not optimal one. Okay, we'll go to the optimal in the next approach. Okay, so for this, in this approach, I'm going to use a heap. Okay, first of all, let's see what we am doing. First of all, I'm calculating the m and n of the matrix. Okay, if you see the cases here, it will be up to 100. Okay, m and n are going to be up to 100. Okay, as simple as that. And all the box content are going to be either a stone, empty space, or a wall. Okay, as simple as that. Yeah, those, this thing I'm calling as a wall, or you can call it whichever you want. I'm calling it as a wall. Okay, as simple as that. So next, what I'm doing, first of all, calculating the rotated box. Okay, the dimension of the rotated box. Okay, I'm doing that. Okay, if you see here, this is m cross n, the resultant box will be n cross m. Okay, the same thing you'll have to do it. Okay, initially I'm keeping it as an empty thing. Okay, but yeah, the way you want, you can keep it in that way. Okay, so some people will say, like, keep everything empty, so like include a dot here, something like that. It's up to you the way you want it. But in my case, I will be traveling the traversing the the dots as well. So yeah, the way you want, you can get up. I am giving this. I'm testing for now. Okay. So this is how the resultant matrix will look like. Okay, just for your understanding. Next, what you are doing now, I'm going to simulate the fall. Okay, see here, just a simulation. That doesn't mean I'm going to change the dimension of the matrix. Here, within the given input itself, I'm trying to change the dimensions. Okay, I'm trying to simulate the fall. So what it means, the idea here is every stone here basically will move towards its right if there is space. As simple as that. Okay. Why right? Because see, the right basically becomes the gravity direction after the 90 degree shift, right? So that is the reason why it will move towards the right. So what I'm doing here, I'm creating a heap basically. Okay. Then what I'm doing, I'm for each row. If you see here, for each row, what I'm doing is I'm starting from the right towards the left. Okay. I'm going from right towards the left. Okay. Whenever I'm finding empty place, I'm inserting it in my heap. As simple as that. Okay. Remember, by default, the heap implementation in Python is a min heap. Okay, the min heap. But if you see what happens in this case, we want it to behave as a max heap. The idea here is, see, the rightmost the index is, the more we have to give a consideration to it. Okay, the more priority it will have. So what I'm doing, see, because I cannot change the implementation of the heap in the library, so I'm just including a minus sign here to make it act as a max heap. But by default, it will be min heap. Okay, I'm just ending a minus sign to the index while doing input to the heap, so ensure that it behaves as a max heap, even though it acts as a min heap. Okay, simple as that. So what is happening, it is doing a heap push here basically. Okay, whenever it finds an empty place, as simple as that. Okay, whenever it faces optical, it will delete every content in the library that is in the heap, and it will start with an empty heap again. Okay, why? Because whenever we get a stone here, for example, if you see in this case, yeah, in this case, if you see the stone, the idea here is after the stone again, you cannot move the stones which are, yeah, the let us see the terms they are using here basically. A stone here and a wall. Okay, so yeah, the idea here is, if you get a wall, okay, if you get a wall, you cannot move the stones above the wall to empty positions below the wall. Okay, simple as that. So that's why I'm doing this part. Okay, so whenever there is a stone, sorry, whenever there is a wall, what you have to do, you have to empty your heap, as simple as that. Okay, instead of like doing a pop, I'm simply discarding it and creating a new one. Okay, next, that's the most important part. Whenever, see, this was for the empty part, this was for the obstacle, there is a wall, and this is now for the stone. Okay, so idea is, whenever we see a stone, okay, what I'm checking whether my heap has an element, that is whether my heap has a empty place. Heap will store empty place, remember that. And how, remember, there is ordering involved. Okay, that is, it will take the rightmost empty place. Okay, first. Okay, it will give priority to the rightmost empty place. Okay, so I will check whether my heap has element. What I will do, I will just do a heap pop. I will multiply with minus one. Why? Because while inside I did a minus one. Okay, so I will multiply with minus one again. Then I will get the index. So this will be the index to which the current element should fall. Okay, so at this particular index, I will go and make it as a hash. What hash represents? It represents a stone basically. Okay, so because the current element is a stone, the index, okay, that is being popped, will be now marked as a stone. Okay, simple as that. And the current index will be marked as a empty space. Okay, so because it's empty space, so I will insert it in my heap now. Okay, that is the basic idea. Okay, so this whole loop will continue for every row. Okay, for every row it will continue. Fine. Now comes the most important one. See, after this part, okay, at the end of this part, okay, let me include a, yeah, print statement also. See, at the end of this particular step, what will happen is, my the given input itself, I've done the simulation. Okay, for what will happen if it falls with gravity. But remember, I've still not transferred the elements of this matrix to a resultant matrix. Okay, because the resultant matrix will have a different dimension. Remember that. Okay, so first we'll see how it looks like, and then we will understand how the transformation I'm doing to the resultant matrix. Okay, so if you see here basically, so we are at example 3. Okay, very nice. We are at example 3. Let's go to example 3 first. Yeah, if you see here in the last row, what is happening is, see, what happens is, yeah, so basically, if you see, there were stones here, and then there were empty spaces. Okay, then there were empty spaces. But what happens is, like in input itself, what I've done is, if you see, the empty spaces are coming to the top now, and the stones are going to the bottom now. Okay, so this is what I've done till now. Okay, next comes the part where we are doing the transformation. Okay, this is what something that I've told you initially. Okay, what we are doing, every box, that is what we are going. We are going to the every index in the box. Okay, this is the every index in the box. This is how it is, and we are going to map it to one of the indexes in the rotated matrix. That is the rotated box. How this is happening, let's see here first. Okay, so if you see here, the first row, please understand my words, the first row is going to become the last column. Okay, the first row is going to become the last column. So what I'm doing, see, here the j is changing. If you see here in this whole thing, here the j is changing. Okay, similarly, if you see the last column, just I can't highlight the last column as such, but just try to see the last column. Here the I is changing. Okay, so the j will map to I, just as simple as that. Okay, so what happens is, see here, the j is basically becoming the I for the rotated matrix. Okay, one thing is very clear. Next thing is, now see here, the only thing that changes is this is the first row. Okay, this will become the last column. There's the only simulation that we have to make. Okay, so since m is going to be telling me the number of, the column, the index for the column. Okay, so I'm doing a -1. Okay, to get the index as such. Okay, because remember it is 3, but we have to take 2. Okay, number of columns is 3, we have to take 2, but this I'm doing m-1, and then I'm doing a minus I. Okay, because the ith row is going to become the last column. That's the reason why I'm doing a minus I. Okay, if the I is 0, then it will do a minus of 0, so it will ensure that the 0th row becomes the last column. Okay, that's how I'm doing it. So let us quickly run this code and see what happens. Remember, this part of the code will remain same for the next solution also, so please pay attention to this will be, helping you a lot, because even if you get the answer without this, you will not be able to submit it. Okay, so yeah, that's how, if you see the output, it's matching with the, expected output. Okay, so what we have done is, let me summarize it once again. What we are doing, we are finding empty place, and whenever we are finding empty place, inserting in my heap. Okay, and since it is a min heap, but we want to simulate a max heap, I am inserting with a minus sign. Okay, and then whenever we are getting a wall, we are, simply making our heap as empty. The thing is, whenever we're getting a stone, we are checking whether my heap has any indexes, which, signifies a empty space right of it. Okay, whenever it is that, I am popping that index, and to that index I'm marking a value of hash, that is a stone. Okay, and then since the current index is empty, I'm marking it with a dot to signify empty space, and then my this particular value should be inserted in my heap. Okay, that's what is happening for each row. This is what is happening for each row. Okay, so this is how the solution works. So if we talk about the space and time complexity, first of all, let us talk about the time complexity. Okay, so yeah, I will start with this. Remember what we are doing, we are going through each row and each element. So basically this row part that is going through each element takes off m into n. Okay, and next thing is, for each element, basically one thing is happening. If you see, either we are doing a push or we are doing a pop. Okay, either we are doing a push or a pop, or sometimes both. Okay, so only in this part we are, discarding it and making it empty. So idea here is, for each element, basically we are doing a push or a pop, and a push or pop in heap takes log n time. Okay, it takes a log of n time. And what is n, by the way? N basically signifies what is the length of the row. Okay, because in a heap, if you see, basically we are going to store at max n elements only. Okay, what is the row of a length, the length of a row? Okay, so that's why log n. Okay, so if you see, that's what is the time complexity, m into n into log n, because m into n is the number of elements, and for each element we are doing a heap push and pop. Okay, so that's how it will be. It will be log n time. Okay, if you talk about the space complexity, if you see here, this is the only space complexity that we are going to use, which is a heap. And heap will store all the elements in a, basically all the elements in a row. In the worst case, remember that, in the worst case, that is, if the whole row is empty, it will store all the elements in the row. Okay, but not in the best case. I'm talking about the worst case. So that is the reason why it will be O of n. Okay, what is n? N is the length of the row. Okay, so this was the approach one. Now we'll go to a better approach. Okay, in this, see, what we are doing is, we are using a heap to, track which index should we put the current stone into. Okay, which index should we put the current stone into? But we, if you like do some analysis, you will get to know that we don't require heap for that. We don't need a sorting for that. Okay, basically, since it is gravity, whichever is the first time to place, and whichever is the next one that we visit, that should fall into that place. Okay, that is the basic idea. So now we'll go to the next approach, in which we are not using anything. We are using not see, basically we are not using any heap in this. Okay, so this can be removed here. Okay, so let's see how it works. The same thing, exactly same thing. I'm creating the targeted box, which is a rotated box. Okay, so what I'm doing here, see, maxi part you can remove from this. This is not needed again. This can be removed. Yeah. So here what I'm creating is, for each row, basically I'm starting a variable called lowest empty space. Okay. That is the space which is, towards the lowest and empty. Okay. So that whenever I've visited a stone, that should fall into that place. Okay. Initially it will be -1. Okay. Whenever it's -1, it signifies it cannot be used. Okay. As simple as that. What I'm doing, I'm going through each element now, from the right towards the left. For each row, what I'm doing, I'm going for right towards the left. Okay. That is, I'm first, visiting the last element of the row, and then I'm slowly moving towards the zeroth element of the row. Okay, so what I'm doing, whenever I find an empty place. Okay, so whenever I find empty place, what I'm doing, see, I'm checking whether the current place, okay, the current place is, more right, or the previous value of it was the more right. Remember, it starts with a -1. Remember that. Okay, so whichever place, see, right, why I'm saying right, because if you simulate gravity, gravity will tell that whether, see, if it falls, it will reach the bottommost place, right? So bottommost place is basically the rightmost place in the untilted, there's unrotated box. Okay, that is the reason why whichever has the maximum index among them, that should be the allotted to the lowest empty space. Okay, as simple as that. Okay, fine. Now whenever we visit a wall, what will happen? So since we have visited a wall, so every string, that is every value after that, to the left of that, will not be able to use the empty spaces after the wall. Okay, so that is the reason why, again, we'll mark it as a -1. That is, we don't have any empty space currently. Okay, so whenever we visit a stone, what we have to do next? See, first I will check whether my lowest empty string is not equal to -1. See, if it is equal to -1, then we cannot use anything. Okay, we cannot use, that is, this particular stone cannot be moved. As simple as that. If it is not -1, that means we have some value to which it can be moved. So we will move our stone to that value. Okay, first thing. Next, we'll mark the current index as a dot, that is empty space. Then what I'm doing a lowest empty space is equal to -1. That is, I'm moving it up by -1. Okay, by see, try to understand why it is -1. If you see the way we are simulating it, see the rightmost place, now it will come to slightly towards the left. So how to simulate that in terms of index? It will be -1. Okay, as simple as that. So I'm just doing a -1 in that. Okay, and then I'm printing the box, and this part is same as the previous solution. Okay, what we are doing, basically we are going through each element in my current box, and I'm mapping it to element in the rotated box. Okay, and then we are rotating the rotated box. In the previous solution I've already explained how this works. Okay, how this works, basically the first row in the unrotated box will become the last column in the rotated box. Okay, that's the idea, and that we are using it. Okay, so let me quickly run this for you. And this works, I've already submitted the solution also. And if you talk about the space and time complexity of this, so the best part is, since the heap is removed, so the space complexity of 1, because we are doing the changes in the given input itself, and the rotated box that we're calculating is for the output purpose. Okay, this is not for our algorithm purpose. Okay, it's not helping us in any way. It's just because the output needs in this particular format, we are returning it. But should not be included in our calculation of the space complexity. Okay, next comes the time complexity. Time complexity, if you see, basically we are going through each row element. Okay, for each row element. So to go through each row element, see, that is the idea, to go through each element of the 2D grid. What we need a m into n space complexity, sorry, time complexity. Okay, so that's the reason why it is m into n, as similar as that. So yeah, friend, that was all for this video. So we saw two approaches. One is using heap. Because of that, if you see, the time complexity is slightly higher. Okay, the time complexity is slightly higher, and because heap in the worst case can store all the elements, that's why it is O of n. Okay, where n is the number of elements in a row. But in the optimal approach, what is up, we remove that heap, because since we are doing a gravity fall, so idea here is, there is no need to sort. Whichever is the last element that we get, empty space having to the rightmost, that is going to be the space that which every stone will fall into. Okay, so we don't need a sort basically to get that. Okay, so we used O of one approach, and the time complexity got reduced to m into n. Okay, which is anyway needed. So if you have a box, a 2D box, and you're visiting each element of it, you need m into n. Okay, this is the minimum most possible. Okay, and the space complexity is a constant, right? It doesn't depend on the input size. Okay, as simple as that. So yeah, that was all for today. I can give the solution in the comment section. Please let me know what else you can think of this. Okay, this was slightly on the easier side, I felt, but it's just simulation. There is no rocket science involved here, no algorithm basically involved here. I just use the data structure to show one of the use cases of the data structure. Okay, the min heap. Okay, so if you are using the solution, you will get to learn something more. Okay, and obviously you can use this particular library if you're using Python. Okay, since this is on the easier side, I'm not giving the Java solution for it, because you can simulate it. Okay, what you have to do is, you have to just create a next array that will be slightly different in Java syntax. That is the only thing you have to do. Rest all things remains the same according to me. Okay, this you can use the libraries to get the max of 2 elements and assemble that. Okay, rest all should remain the same. And yeah, friend, that was all for today. And if you like my efforts, please do subscribe to my channel. It really gives a lot of motivation to continue further. See you tomorrow. Thanks a lot. I'm hoping that you will subscribe my channel.